Hey everyone, and welcome to The Explainer. Today, we're going to crack open one of the most powerful tools out there for figuring out how the world works, the scientific method. Seriously, think of it as your ultimate recipe for discovery. All right, let's get into it.
You know, it always starts with a simple question, doesn't it? You're just living your life, you look over and you notice something. Maybe one of your plants is loving life, growing like crazy, while the other one, not so much. And you just think, what's the deal with that? That little moment of curiosity, that's the spark for everything we're about to talk about.
And this is the tool that turns that I wonder into an I know. The scientific method isn't just for fancy scientists in big labs. Nope, it's a step-by-step game plan that literally anyone can use to get real, reliable answers. It's all about having a solid process for testing your ideas.
So, why do we even need a whole process for this? Well, it's all about keeping things fair. This method forces us to use actual, measurable evidence instead of just going with a gut feeling. It helps us keep our own biases out of the picture so the results are accurate. And, maybe most importantly, it gives us a clear way to share what we found so other people can learn from it too.
Okay, so let's get into part one, planning your investigation. Because honestly, every great discovery starts with a really solid plan. This is the thinking part. It all happens before you even pick up a beaker or a ruler. This is where we build the foundation.
So here's the basic blueprint. It kicks off with an observation, noticing your SAD plant. That leads to a little bit of research. Maybe a quick search tells you plants need light. From there, you form a real investigative question, like, hey, does the amount of sunlight actually change how a plant grows? Then you make your hypothesis, which is just your prediction. And finally, you figure out your variables. Let's zoom in on those last two, because they are super important.
A hypothesis is way more than just a random guess. It's an educated, testable prediction about what you think is going to happen. A really awesome way to write one is using that if-then format, like, if plants get more sunlight, then they will grow taller. See how specific that is? It sets up a clear cause and effect that you can actually go out and test. Okay, now this right here is the secret to a fair test. You've got three types of variables. The independent variable is the one thing you decide to change. For our plants, that's the amount of light. The dependent variable is what you measure to see if your change had an effect. So we'd measure the plant's height. And then you have your controlled variables. This is everything else you have to keep exactly the same for all your plants. Same pot, same soil, same water. That way you know for sure it was the light that made the difference and not something else.
All right, our plan is solid. Now it's time for part two, running a fair test. This is where the rubber meets the road. We're moving from all that thinking and planning into actually doing the experiment.
Now, when you're doing the experiment, one word is key: precision. You made a step-by-step procedure for a reason, so you got to follow it to the letter. Write down everything you measure and be super careful about it. And please, remember your units. Is that 15 centimeters or 15 inches? It makes a world of difference. Details matter.
After a while, you'll end up with something that looks like this, a data table. And this is great. We've got our numbers all organized, showing the plant height over 2 weeks. But just looking at it, can you instantly see the story? It's kind of hard, right? The numbers are all there, but they're not exactly jumping off the page.
And that's the perfect lead-in to part three, visualizing your data. This is where we get to be a bit of an artist and a detective. We're going to take those boring numbers and turn them into a picture that tells a story. This is how we find the patterns hiding in our data.
Exactly. The table is accurate, but our brains aren't really wired to make sense of big blocks of numbers. To really see what happened, to understand it in a split second, we need to visualize it. We need a graph.
So for the kind of data we have, where we're comparing a few separate groups like full sunlight, partial shade, and darkness, the perfect tool for the job is a bar graph. It's literally designed to compare things in different categories.
And bam, look at that. Isn't that a million times clearer? You don't even have to think. You can just see that the full sunlight bar is way taller than the others. The story of our experiment is right there, clear as day. So much better than just a table of numbers.
Now, what if you wanted to see the growth as it was happening, not just the final result? That's where you'd pull out a line graph. We could take all our measurements from day 1, day 7, and day 14, plot them as points, and connect them with lines. That would show us the trend of the growth over time.
Okay, so we've got bar graphs for comparing categories and line graphs for tracking changes. What if you want to show how one thing is made up of different parts, like parts of a whole? For that, my friend, you want a pie chart. It's all about percentages and proportions.
A perfect example is the air we breathe. A pie chart, or this donut chart, which is basically the same thing, instantly shows you that our atmosphere is mostly nitrogen, with a decent slice of oxygen and just a tiny sliver of everything else. It's the best way to see how a whole is broken down.
Now, quick detour, because this trips a lot of people up. A bar graph and a histogram look alike, but they're not twins. Bar graphs, like we saw, compare separate things, so there are gaps between the bars. A histogram shows you how often something happens within a continuous range, like how many students scored in the 80s versus the 90s. The bars touch to show that the numbers flow from one range to the next, no gaps. Okay, we've done the experiment, we've visualized our data, it's time for the grand finale. Part 4, drawing your conclusion. This is where we finally get to answer our big question. So what? What did we learn from all this? And a good conclusion is straight to the point. You just state what you found based on your data. Plants in the sun grew the most. Simple as that. Then you have to connect it back to the beginning and say whether the results support your original hypothesis or not. You've got to close that loop.
But wait, we're not quite done. The best scientists always take one more step: evaluation. You look back at your own work and get critical. Were there any weak spots? Could something have messed up the results? Like maybe the temperature wasn't perfectly the same for all the plants. Thinking about how you can make the experiment even better next time is a huge part of the process. Science is all about improving.
And that's really the main takeaway here. The scientific method isn't some boring list of rules you have to follow just for science class. It's so much bigger than that. It's a powerful toolkit for thinking, for solving problems, for figuring stuff out in pretty much any part of your life.
So there you have it. You've got the recipe, you've got the toolkit. The only question left is, what are you curious about? What's the first thing you're going to investigate? If you're looking for more science tips or ideas for your next project, you should totally follow Mr. Chi on Instagram, TikTok, Facebook, and YouTube. And hey, if you like this explainer and found it helpful, do us a favor and hit that like button, share it with a friend, and subscribe for more. Thanks for watching.